Okay. It's coming or not? Projector is off.
No.
So. Well, so while this is coming up, let me welcome you again to this historical course offering. So together, I think we can achieve a lot. So just to let you know, we have a new tradition here. Every lecture, in the beginning, you will have a quiz like this, very simple. Okay? And in the end, you should be able to quickly fill up. It's supposed to be easy, quick, and some checkpoints about the key concepts you are supposed to know. Okay? But in the beginning, maybe you feel, I don't know, but it's fine. Okay? So what's left? For the last lecture, I got a question and you get a time answer you about grading policy. Okay, grading policy. So the grading policy, we can go through from here, the part of the syllabus. There is a percentage distribution regarding our course. Right? Is it last section? Yeah. Grading policy. Yeah. So you can see that you come over here every time and you did the quiz, it shows up when you physically are here. Then you earn 10% already. Okay? Divided by, so every time you fill out this one, you get maybe 0.05 point towards your 100. But anyway, I'll use this one. So basically, if you come all the time, do the quiz, doesn't matter, you leave it blank. Okay? You don't know, it's okay. You didn't fill up correctly. Don't feel pressured. It's okay if you don't know how to fill up. But you should be able to fill up all the blanks in the end if you listen carefully. And sometime I'll let you know, oh yeah, this is all quiz. So it is that simple, right? But the first one is sort of checking how rusty you are regarding those signals and systems. So if you feel like doing those simple programs, you still feel difficult and have no clue, you really need to pick up signals and systems by going to the online OCW, MIT OCW, open courseware. And it's a very good collection of lectures. So you can understand what is considered as a signal, classification of signals, and how the operations of signals, systems, signal systems. So those basic knowledge, I really don't have time to cover those. It's a separated course, okay? But we are going to cover fractional signals and systems. So don't worry too much, and we are going to go through those again, all right? And labs, you may feel, where's the lab? I'm going to send you a lab description. So every 2 weeks, you are supposed to have a comprehensive lab. Comprehensive means it will take you 2 weeks to finish. But my expectation is your focused 6 hours should be put on the lab. 6 hours, the encoding, programming. So that's the expectation. That's a hardcore 6 hours. However, you are expected to do one by one, one-to-one. Like preparation 1 hour, do the lab 1 hour. So together it's like 12 hours. Supposedly 12 hours for a lab. That includes the doing the lab, reading the background material, and writing a report. Okay. Our first lab will be on Metag-Leffler function and those asymptotic analysis, computational experience for that. So I'll write up all the lab and the requirements. You do one by one. Okay. It will be very interesting. Okay? And you will understand using what kind of tools you can do the computation. So labs, 8 labs. So you earn 4 credits because you do the labs. And those labs are mostly computer simulation based. I originally planned to have some lab experience. So you do some real lab, collect data, do experiment on the system, fractional order system, then you get the data from the fractional order system, then you do modeling or do analysis. Okay. So, but I was informed that graduate students, graduate class are not supposed to use too much real lab resources, and there isn't a budget for it. And you don't pay lab fee, do you? Yeah, you don't. So I changed the idea. However, individually, some of you may have some lab access in your research labs. And after discussion with me, probably I can allow you to do the real experiment on the real system and to see whether you can do it. So, but otherwise, we just focus on the simulation based, okay, which is okay. Another idea is to do physiological signal processing. So you breathe and you walk, you have gait, your heart beats, pulse. All these signals are generated from complex systems. Okay, so they must carry some fraction order dynamics behavior in it, which is true. And Marvin Cole and also John Liu here is doing some things on this. So in that sense, if you want to do experiments, press your pulse here. Okay, so we have some ideas to do. But I'm open. If you really want to do real systems, I have some ideas. I have my own lab resources, but I cannot do a uniform in our lab in there. That's why I said if you have lab conflict in time, ignore it. I give you the flexibility to do a computer-based simulation, meaning those data from complex systems are already collected. Okay, you don't have to go there and collect it again. You collect it and you play with the data. So, questions about that? There's a very important component. Because lab, if you do 8 labs, you only earn 25% of your, so 1/4. And there's another one is FISP, stands for Focused Independent Study and Presentation. So you need to produce, you read a focused topic. So write a paper-like report and do a professional level presentation. Okay, that will be 20%. In the midterm, in the week 10, I'm going to give you a take-home exam. That will give you a chance to systematically summarize what you have learned. Okay? Otherwise, you always feel a scattering of the knowledge here and there. But then you have take-home, you understand what I really need to learn and connecting all the dots. Okay? And every week we'll give you homework. It's approximately 15 times. Okay, it's pretty demanding. Then that is about 30%. Okay? The homework questions will be all from the fractional calculus by engineering here, majority of them. Okay, so it's good to have a book. And in the homework questions, they may refer to the text. So it's better you have the book so you can read. Okay? From the homework, you will understand what are the contents for fractional calculus. Okay? So this is a good book. And another good news is I have all the solutions of all the questions. So I'll select some of them for you. I don't want you to do everyone. So average load is 1 question per day. Okay? So some of them are really simple and straightforward. Some of them you need to refer back to the text and read it. So as you can see, I'm not going to go through the book with you. You are supposed to read the book. Okay? Like chapter 1, like chapter 2 of this book and chapter 3, the PDFs are already uploaded. So you can start to read. And I already uploaded a homework question for week 02. Week 01, I hope you can finish by Thursday. For those of you who want to earn credits, please follow the rule, okay? If you are late without a reason, then that's 0. If you tell me that I'm going to be late because of reason X and Y, Z, then probably it's okay if you plan in advance. If you have a delay without a reason, then it's a invitation to get a 0 for that specific one. Okay? Well, so any questions regarding homework? From this, you can see we are going to have 8 labs, about 30 quiz, about 15 homework, and also 1 big project. So the first homework 1 is already a hint about what are you going to focus. What are you going to focus for the FISP project? So you will have about 10 weeks to think about it. I really hope you focus on the FISP after week 10. But if you want to do right now, I encourage you to do so. Some of my own students, they already had good exposure to fractional calculus, so they can start now. But for some of you never heard about it or just recently heard about it, don't have a systematic exposure to fractional calculus, I suggest you don't rush, okay? Have the basics in place first so you understand what you really want to attack. Okay? So don't rush. And my objective is, again, I want to repeat, is in the end of this course, based on FISP, based on what you learn in this course, combined with your research project and research direction and research emphasis, your work is at a publishable level in Tier 1 professional journal. Okay? Tier 1, not Tier 2, please. Tier 1. Tier 1 meaning world-class journal instead of pen. You know what I mean? You know, we don't want to do that. Okay? Any questions? I'm going to really start the lecture. I actually prepared it very. I took a long time to So this is our series lecture starting on the second lecture. The first lecture basically to go through the administrative details, okay, for this course and getting to know everybody. And we have 10 slots for registration, and I think we have 10 registered. So it's a full load. I feel very proud. Anybody who wants to come in, you're fine, but you have to audit. You cannot earn credits, okay? You just audit. And if I didn't invite you, I need to do, Kevin, I need to add you on our list. Yeah, all of you in this room, I'm going to invite you to the class list. So anything I put it there, you'll get a notification saying, oh, I just uploaded a file. Well, so this is our basically first lecture. So I plan to have 3 modules for the motivation part, okay? The first module is regarding the general motivations. That could be open to high school students. So it will be easy drive today and not much challenge. So as you can see from the quiz, the question is very, very simple. But you don't understand how to answer it, not a problem, don't worry. In the end, I'm 100% sure you will be able to answer it. And unless you're sleeping all the time. So it's very difficult to come over here in the morning at 9 o'clock. I understand that many of you struggle a lot. I appreciate. I feel proud of you, everybody are here. So that gives me also more motivation to put more time to get more prepared, and so that we have more outcome of our learning. So appreciate your efforts. Okay, coming over here. Okay. And late 5 minutes is fine. Okay, don't worry about it. Okay. Sometimes traffic. Well, hold on. I'm going to. But I want to make an edit. Let's find out I didn't do right. Our ME program used to be MEAM, called Mechanical Engineering and Applied Mechanics. So we deleted Applied Mechanics. It's not because Applied Mechanics is not good. Because Applied Mechanics is part of a mechanical engineering. We don't really call that. That shows our logic issue about thinking. So actually, I'm a member of ME and ECS. I'm also a member of SNRI, Sierra Nevada Research Institute, and UC Solar. So I'm affiliated with these 4 units on campus. So just to show my respect, I better put all of them on. Okay, so I forgot to edit this one. So you can see FOT is your last question, is fractional order thinking, your quiz. Already? So I want to really start with this slide I put together. And sitting in this course, we know that fractional order mechanics is based on fractional calculus. But if in a barbecue party and people and you mention a fractional calculus, then what is fractional calculus? So what are you going to explain to people? I suggest you probably explain this way. So, oh yeah, fractional calculus. You know, you learn calculus is integrating and differentiating. That's combining calculus. But fractional calculus basically is integrating and differentiating. It's a type of non-integer order. So this is the middle. All right. So in other words, the orders can be a real number. And actually in the literature, if you check carefully, the orders could be a complex number. Okay? Any number. Okay? So the orders are not constrained to be integers. In fact, it's not constrained to fractionals too. Because what? Using the fractional is just the abuse of terminology. in precise way, we should call it non-integer order calculus.
How
So-
about the rational calculus?
So, sorry,
Rational calculus.
rational?
Yeah.
Yeah, we. Yeah, it's called fractional. Is because of historical reason. They only started those rational numbers. So, but they didn't call it a rational calculus.
Yeah.
That implies previous calculus was not rational. So, irrational is not a very good word. A good point. I like it. So you can see, I learned from my class, and I like this intellectual interaction. Very good. So, so the question is, why this is black? On my screen, this is red.
Color is not enough.
It's interesting. So the question is, the guy in the conversation in a swimming pool or in a barbecue backyard. So how this is possible, you know? The differentiation of 90 order, how this is possible? It's pretty natural, you know. You know? Why should I care? I don't care, you know. Why should I care? Okay? And so you sell this one to me, then anything good for me, you know. So this is a very natural question that you have to address, right? Okay. This lecture is going to address all of them. Okay? So this type of explanation to regular people, okay, who are not very well educated or not well informed, need a kind of question and answer session. Okay? So I'm going to guide you through that. Okay? And so I want to apologize. Many of my students already have seen the slides more than once. So like it's already at the medium to advanced level of doing good research on this topic. So you should bring something else.
More systematic.
Okay. But anyway, so I think this is a good starting point. Okay? Every one of you here today taking my class, and you should be the ambassador for fractional calculus since January 1, 2014. Okay? You have to become like that, a promoter, advocate of the use of fractional calculus. So the reason is, this type of, from integer to non-integer type of thinking is embedded in our mind. We didn't realize. Think about when you are an elementary school student, you will learn about those integers. Then you learn something in between integer, non-integer, like rational number or stuff like number access. Like my son is in 3rd grade. He started to learn about this number access. And of course, they learn multiplications. So 2x squared is a 2 of x multiplied together, x cubic is 3 of them. But you know, at the middle school level, you probably cannot remember at what point that power n actually can be anything. Okay? It's a generalization process of your learning. So there isn't anything question. No question asked. Did you ask how this is possible? N is non-integer. You didn't ask that. It's pretty naturally generalized. You didn't realize. Is that right? But you just cannot remember when that happened in your mind. But generalization happened. Same thing. Probably some of you already know. The factorial and gamma function is another pair. Factorial is an integer type of thing, right? But n has to be integer. But generalized factorial is a gamma function. They have the same recursive type of relationship. Okay? So this is from integer to non-integer. We already touched the experience in our education history. We already touched it. Okay? So Next one is Mandelbrot. Not long time ago, 70s, 80s, they start to use the dimensions. We know we are living 3D dimension, right? But is there anything on non-integer dimension? I think today everybody agrees this. Dimension could be non-integer, right? So you got sponge, is this 3D? Probably not. Okay, probably not. But in generalization, is your muscle 3D? I don't think so. It's soft. You know? So there are some interesting things there. It's linked. Non-integer order objects. Non-integer dimensional objects and fractional dynamics. There are some intimate relationships. We will come to the point later on. There is a connection. It's called fractal geometry. Fractal geometry. Okay. So now we come to calculus. So if we write down the integration and differentiation and arrange it in this way, then naturally the last line will remind you this number. Okay? So it's pretty natural to ask a question about what's in between. Okay? What's in between? Pretty natural. Is there anything strange? No. But you don't have to ask today. It was asked more than 300 years ago. Okay? 1695. L'Hopital asked Leibniz a question. What about I have a half derivative here? What's going on? You know? So that's we have a slide about this. Okay. So you can see this kind of in-between thinking is everywhere, and so we also call this is a fractional order thinking when we come to the dynamic system. Okay. There are many other examples about this kind of in-between thinking, so that we can generalize concepts and methodologies and signs, generalize it to a new height and gain popularity. The most important thing is the fuzzy logic. Okay, how many of you have heard of fuzzy logic? Yeah, if you buy a rice cooker and you cook it, most likely there's a sticker saying that a neural fuzzy, okay? Neural fuzzy. Some fuzzy stuff, control strategies inside. So they cook in a fuzzy, intelligent, control way, so they cook the rice is the best possible. So I used to have a picture of it, I forgot to put it here. But anyway, so that's called fuzzy logic. In fact, the splines, if you learn about these splines, there are also, you have quadratic spline, cubic spline, and so on, of course. It's generalized to fractional order splines. It's about 10 years ago. It's only about 10 years ago. And also moments. You know that you got a random, you got time series, random series. Then you know how to do an average of all them. This is already a first order moment, is it? Or zeroth order moment. I think it's considered as zeroth order moment. Okay. And so you have a variance, that's a second order moment, right? But what about 2.5 moment, 1.5 moment? So those kind of fractional moments are becoming very important for non-integer order moments. So in fact, this I need a separate lecture on this. But unfortunately, I don't have time to cover all the stochastic fractional order, stochastic nature of the process. In this course, we are mostly focused on deterministic framework. Okay. In the stochastic world, this is very important. This is very important in the sense that some of the man-made and natural sequences of random processes, the second order moments do not exist. Okay? Do not exist. this caused significant consequence, making the well-known least squares type of minimization invalid. I don't know if you can understand. So you try to minimize something that guy is supposed to be infinite. You minimize the variable. That variable is infinite. You minimize the infinite. What does that mean? So I have a slide to tell you how important this is. In fact, the random process, only the fractional lower order statistics exist. So FOLOS stands for fractional lower order statistics, meaning the second order moment does not exist. It's an infinity. While you do least square, then you try to minimize the infinity. So that doesn't make sense. Okay? And they will create, although numerically you can do it, that may create misleading results. Okay? It's very serious. Okay? We talk about fractals, and I'm going to show you two slides regarding fractional Fourier transformation. So time and frequency, you know that you can always do FFT of the time, fast Fourier transformation of the time sequence, then you get the spectrum. I assume you have that knowledge already. That's part of the signal systems. Okay? You do FFT, Fourier transformation. But what if you do FFT of this, you get another array, then do FFT again, do FFT. Keep doing FFT, you'll come back after 4 times, you know. FFT, then you got frequency. You do FFT of this frequency, you got reverse time. You do again, you get another FFT. Then you do again, you come back. So it's kind of interesting thing. I'm going to show you why this is so interesting. For non-integer order calculus, or the fractional order calculus, it's an abuse of the terminology. Another thing is we use FOC, it's a fractional order control. So when we talk about fractional calculus, we usually don't use the order fractional order calculus. Because that would give you FOC, then it's confusion about FO controller or FO. So usually we use applied fractional calculus. Because we learn it, it's going to apply this math tool to solve some interesting problems in a new way, getting new insights and getting new and better results. So this is basically to share with you this kind of fractional thinking. To justify that going in between is also very natural. And actually in Chinese philosophy, going in between is called 中庸之道. Okay, you don't have to spell it. It's already there in the literature long time ago. So you should not go extreme, you should go in the middle. Okay, so I think that so far it's very soft, but I can expand each bulletin, talk all the time. But I would like to share with you something regarding fractional order Fourier transformation. So let me show you this one later. Let me show you this one first. So you got a signal. So this is basically signal energy is in here. The noise energy is in here. In the time frequency expansion, you'll see the signal energy concentrated here, noise in here. So if you do, this is time, that is frequency, okay? You do time domain analysis, you can see this and this are overlapped, so it's hard to separate them. If you do frequency domain analysis, it's also difficult to separate them because they are kind of mixed. So somehow you can do a fractional Fourier transformation, go in between time and frequency. So then you do the signal processing along this, transform the domain, fractional Fourier transform the domain. You will see the signal and noise projection are separatable. Okay? Okay? So that's the beauty of fractional Fourier transformation. So usually you do the signal processing in a transformed domain. Then you can gain good result. So let me show you an example. So you have original signal, okay? So in this original signal, what you do is in ordinary Fourier domain, okay? So this is the distorted signal. Signal plus noise, you got this one, distorted, okay? Then what you do is this is the signal you want to do filtering, so you recover that. So this is integer order Fourier transformation. So you do Fourier transformation of this signal, this time domain signal. This is the frequency domain signal. Okay? So you can see multiple peaks. So it's pretty overlapped. So you try to chop something off, fine, you can do it. Then the filter signal will come like that. So this one and that one has big difference. However, if you do a transformed domain in a fractional Fourier domain, you will see in that fractional Fourier transformed domain, there are two peaks. And actually this peak corresponding to the signal, and this peak corresponding to the noise added. So there is a pretty clear cutting here, so you can just use a low pass to chop this one off as possible. When you chop this one off, then the recovery signal compared to this one is pretty close. So just think about this. This is integer order signal processing. IOSP. Okay? This is FOSP, fractional order signal processing. So visually you can see the difference. So we can say this is one of the interesting outcome or consequences of using fractional order thinking, right? So these are all in the literature already is proven. So when you are reading it, you cannot publish it, sorry. So it's already there. So
I'm curious, do we need a fractional filter for this, or can we use integer filter to filter the noise?
Yes, you can use integer order filter to filter the signal, but can you really get this result?
I mean, you said we can use a low pass to filter.
Low pass is integer order. It's integer order. It's just like you transform the signal into the fractional signal. But the filtering here is still integer order. There's a different concept here. So you just do it in a fractional domain process, while the processing itself still could be fractional, integer order. Okay? It is after transformation. So in fact, this is a slide I like, and they put a title as a conclusion of the talk. It's basically the take-home message. It's from Richard Megan, who is the author of the book, our textbook, and he will be here December 5th and give us a guest lecture in this class. And again, oh, by the way, did you check the textbook? How many of you already got one? Not yet? You got one. How come you got one? No other people. Have you checked?
But you say after 10 days.
Yeah, it's supposed, but I heard different things. They already have some.
Yeah, I got mine at the bookstore.
I suggest you go and check. Give them a pressure that there is an urgent need. Okay? So, you know, in real world, the four-letter word called wait, W-I-T, is needed. Okay? You just wait there and nothing will automatically happen. You have to pursue it. Same thing as like this text. Okay? All right. So this called famous Richard Megan's range. So you can see, he said this is fractional characters. That is the integer traditional characters. So you have to use a different order in a different integer case. While fractional order, you can do continuously adjustment. Okay? See that? See that? So I like that. So this is very good illustration of going in between, or generalization from integer to non-integers. Okay. And my PhD student Calvin Koopman also gave an interesting picture. Everybody knows the mountain bike. So you have a different speed, so you can change it. So that's integer or the calculus is discrete. So while in this case you have a transmission that can change the speed in a continuous way. So he said that is integer or calculus. This is I think Zoro also created something.
Hierarchy.
Oh yeah, maybe I should show that one. I think Zoro created something here. I forgot to put it here, but let me try. Yeah, I think it's here.
Not in this one. In the
Second.
No, it's in the fractional topic state.
This one has it. I saw that. No.
Maybe, yeah.
Yeah, you have it. I remember I saw it here.
Oh, yeah,
Oh. Is this the one?
yeah, that.
Yeah, this is a hair cutter. You can put the.
I have one of these. Dr. Liu have one of that.
Okay. So that's a fixed one, right? You don't have adjustment about the distance between the teeth. But this one has a handle here. You can adjust it, so you don't have to use this type. I think it makes sense. I'll try it to your notes in the future.
Probably maybe Dr. Liu there also.
But if you delete, oh no. So it's okay. Well, this is kind of funny. I like this type of notion. So remember, this is a module. Today we cover general motivation to answer questions raised in the public party. So this is pretty accessible, is that right? So we give you a talking points to make analogies that you need fractional calculus. So answer the question about why should I care, you know? So this is possible. I think I already convinced you it's possible. You already did experience something similar in your middle school, so like x to the power of n, right? So it was born in 1695, and Leibniz invented this notion, okay, notation, okay. So L'Hopital asked, what if the order is half? Leibniz actually answered the question a little bit longer, as I quoted in the longer paragraph in there, quoted in the book, so you can see Dr. Richard Megan is really good. He went to the literature and pulled out the original answer. So this is a simplified version. Simplified version. So Leibniz said that someday useful consequences will be drawn. So you know how to fill the blank. So the quiz is like that. Simple. I even give you the hint. Okay? But you put it there and you collect again. You have 30 pages of this thing put together. It's a good memory. Okay? I'll do my best to have a good experience. Every lecture you have this good quiz. Okay? All right. Okay. So one comment. You know, Leibniz was an enemy of Newton, Isaac Newton, right? Both of them claim they are the first to have invented calculus. Okay? Newton used differentiation of x dot, f dot, f double dot, f triple dot kind of thing, and f bracket, kind of thing. But I think now more people are using this notation. So notation is important so that you can ask good questions using the notation. So this is called notation is important so that they can ask what if n is half. But I think I used this told you many times. Some of you heard about it. Using Newton's f dot, you cut that dot, you got two dots. So you cannot ask this type of question. So notation is important. And in fact, Leibniz to even Euler, they touched, okay, they researched on fractional calculus, okay, long time ago, 300 years ago, okay. So I think all those, today we look at this one is so simple. So Leibniz, they started a non-integer value of n for the definition like this. They believe that this is true for all the non-integers. Okay, and Euler also figure out how to generalize this integer order differentiation. It's basically the power function x to the power of n for m, then n's derivative. You will have this type of notation. If they introduce the gamma function, so then everything still will be true. Then if you take you have a dx half derivative of x, I think Euler is the first person to make it correct by solving this. So he's the first person making a half derivative of x like this. Simply going through this type of generalization process. And of course, he introduced the Euler gamma function. Gamma function he invented. And gamma function is a generalization of factorial. Okay? Factorial. So you can see all the great minds in the past always ask whether we can generalize from non-integer to non-integer. So return back to your subject of study. Is there any integer part can be generalized to non-integer part? That is the question you are supposed to ask since last Thursday. And you are doing homework 01. It's basically I stimulate you to ask this type of question. Okay. So what is it look like? So if a function of f of t, what's the alpha's derivative? Okay. The answer is, it looks like this. This is called Riemann-Liouville definition. So you have a function, you do divided by t minus tau. Let's assume n is 1, okay? So you only start alpha is between 0 to 1. 0 to 1. So that will make things easier. So you got the 0 in here, you get the power of alpha, This is much easier to think about it. So this is, n is 1, so you have differentiation in here. Okay? Right? So this is pretty interesting. In other words, you can see the f of tau was weighted by another inverse power law polynomial. And it's in the convolution format. So it's like a function convoluted with a specialized corner. That corner is 1 over t minus tau to the power of alpha. Kind of convolution.
Professor, is the subscript of d is a or alpha?
It is a. That's a very dedicated question. We cannot elaborate at this point. Let's assume that alpha stars, that's A. It's called initial point, initial value, initial point, okay? Initial condition. So when this alpha is specified, you also have to specify that function's condition at that point. For dynamic system, that relates to initial conditions. Okay? So I'll come back to this question later on, because that's very, very interesting also.
So, Professor, if we assume that the change in d of f of t is different from d of t, is that possible? I mean that alpha in the numerator and denominator is different?
If alpha is 1, then it's full differentiation.
I mean, assume that we have d of f of t to the power half, for example, and d of t to the power 1/3. Is that possible? Does it have a meaning?
I know what you are trying to tell me, and so this actually people were talking about this one a few some time ago. We are talking about we do a d 0.5x dt 0.5. So isn't this a possibility that I put 1.5 here? Well, this is alpha, this is beta. Are you talking about this?
Yeah.
Okay. This is already published by a person I know. They call this one fractal derivative. Okay, fractal derivative. Not fractal honor, it's a fractal. He has some interpretation and justification why this is needed. Basically, in the generalized sense, your time and space can be different in a different fractal nature. Time and space in a fractal nature. So it's not an Einstein's uniform type of time-space. It's fractal pieces or fabrics. In fact, he used a fabric about this. Okay?
Does it have application?
Yeah, there's an open publication in journal paper.
I mean application in reality. Can be used to model something.
Yeah, he used this one to interpret the turbulence observed. Okay, so check the paper by my friend Wen Chen of Ohio University. So if you do the search, you will find him. Okay. So I like this type of question. So good research is usually from asking good questions. And remember that there is no stupid questions. Okay? No matter. Okay?
Well,
There are only stupid answers.
actually, at the beginning, I thought my question is stupid.
No, there's no stupid question. All questions are smart. Okay? So, don't worry about it. Don't worry about asking questions. There are some good questions. There are some questions. There's no bad questions, no stupid questions. There are only bad answers and stupid answers. Okay? So, actually, Gromov-Letnikov, they gave a definition. And that's a generalization of the finite difference type of idea. Okay? So you learn about fractional, about the finite difference. You have ft minus h divided by h. Okay? So then you have h is to the power of 1. That's the first derivative. But if you have alphas, then you have h to the divided by h to the power of alpha, then send h to 0. Then this is what? This is a bracket to the power of alpha, right? So that's then you expand, you have infinite long, and you try to truncate. So that's the Gromov-Lebednikov definition.
So, Professor, this definition with the previous definition are the same? They are equivalent?
They are equivalent in certain sense. But if everything in the initial matters are initial conditions. If in the initial condition is 0, then we can see easily they are the same. However, from application point of view, this kind of continuum form, okay, is good for analysis. This is a discrete form that is easy for computational analysis. So both of them are useful. Of course, there are many other definitions of fractional calculus. So I only want you to remember these two first. So
Can you please show the similarities between these two definitions?
you don't see similarity at this point. You don't see it. You only can see when the asymptotics set h to 0, they are equivalent. Yeah. Okay. So we talked about definition. We have seen this definition. We're going to play with this one again and again. Okay, again and again. So so we return back the question about fractional calculus. Why should we care? You probably cannot answer it properly. What it is, you probably can explain now. And why? What is this possibly meaningful? So you can address that question. But why, why should we care? Is there anything good to us? So I have something very interesting to show you. In fact, Leibniz already said useful consequences will be drawn. Okay, so I plan to show you a few useful consequences. One of them is 2011. We have a paper. It's called Tuning and Auto Tuning of Fractional Order Controllers for Industrial Applications. It's published in Control Engineering Practice, that journal, Elsevier's journal. It's a top journal under International Federation of Automatic Control. And this paper gained top citation. If you go to the web, and there's a top 25 cited papers for the past 5 years, you will see we are number 1. And it's been there for more than 1.5 years, or maybe 2 years, always number 1. Meaning that draws a lot of attention. People are following and doing the work and citing our work. So all this is an evidence of good consequences. So they gave $500 as a cash award at IFAC World Congress. That World Congress only happens every 3 years. 2011 was in Milano, Italy. Okay? And 2014, every 3 years. 2014 will be in Cape Town, South Africa. And 2008 was in Seoul, Korea. 2005, I forgot. Oh yeah, in Prague, I was there, where I met Rudolf Kalman, Kalman Filtering. He gave a talk. I'm sitting just like this distance. So. And his first slide of the talk is very interesting. He said, first slide, putting the physics right. The rest is mathematics. Very interesting. I don't have time to tell you more. But anyway, this is I feel very proud of it. Okay? So, and we also published some papers. It's accumulation of about 10 years and 5-6 years. Fractional order system controls, fractional signal processing. All these 2 books, you can get a PDF for free. Okay? from the web. Go and download it. So if you want to save time, I can download it for you. I already have a PDF. So let me know. And most recently, we published a book, Distributed Order Dynamic System. I feel this book will catch lots of attention. And also, again, this PDF is available. And fraction order motion controls, we published a book about 400 pages, dedicated for motion controls, okay, for machines. And Dr. Law, my previous research student, and he is working in the motion control industry, and he's applying this on everywhere. Okay? I believe. And most recently, actually in last month, August 4th, okay, a month ago, less than a month ago, in Portland, Zhou already digested all the pages and put together a set of slides to cover everything in this book, okay, so that you can learn this book in half a day. So it's called pre-conference half-day workshop. So the set of slides we're going to share with the class. Is it okay? Okay. So there you can see the level of understanding Zhou already has. And probably he can be a good point of consultation if I am not available. Okay? So they can ask Zhou some questions. I think Zhou is already at a different level of understanding of using fractional calculus to control identification. So you already learned in the past 2-3 years. When is your first time you heard about it?
2011 when I joined your
and so I think we're making very good progress, and he's doing research and doing something never been done before. And also, we hope it can be used in industry. Okay? So all these are good consequences. So next slide will be yours. So I said, yeah, you cannot remember what I showed. There are so many consequences, but at least one you can remember. That is the present course is one of the good consequences. So I cannot say that I moved from Utah to here is just for this course to offer to students in an official, formal way. I don't want to say that way, but it's almost true. Okay? It's fractional reason of my move. Okay? So that's the good thing of a new university, and the openness without a war between disciplinaries. So that's good. So everybody here should feel a level of luckiness. Okay? So we can meet in the class. It's not easy. However, it's predicted by Leibniz already. One day good consequences will be drawn. So this is one of the many. Okay? So now you know how to fill the blanks. Well, talking back, you will see that there isn't a need to distinguish between differentiation and integration. It can be unified because the order, differential order, if negative, then it is integration, right? You know it already. So you have a unified notation, and this unified notation can be just our starting point. So whenever you see the D does not mean differentiation anymore. You know, it's generalized differentiation. You know, remember that. So, but however, in the literature, people are still using I for integral, D for differentiation. So, from my point of view, there isn't a need to invent another notation. So I'll give you a quick idea about what it looks like. Let's look at this one first. this axis is time, so we're doing sine t, so t. So the origin is 0, and this axis is the order. So 0's order derivative, then is sine. Can you see sine?
Yeah.
Yeah. So then, first order derivative you can see is cosine, right? So then what's in between? Yeah, this is exactly in the shown here. Get a feeling, okay? So we can do the same. So this is a unit step. So you have order in here. This is time. So this is the amplitude. So you have constant 1 in there. So it's called Heaviside. But we usually call it a unit step function. Okay? Unit step symbol. So then you will see first order derivative will be 0. Okay? But what's in between? There's something in between. Can you see? But there are something messy here. This is called singularity. Okay? So you have something divided by 0 there, singularity. But don't worry about it. Okay? It happens. So in fact, you should be able to reproduce these figures. Okay? Okay. So if you cannot, you should ask, what code I can use to reproduce this? Okay. So questions like that. But you don't know how to do. That's very natural. But in the end of the semester, you will say, wow, this is a piece of cake. So now let's take a look. Can you see clearly? So you have a ramp function. First derivative will give you a square wave. Half derivative will give you something in the middle. Derivative of 3/4 will give you something like this. Okay? So the question is, with fractional calculus, and why should I care? One important thing is you are smart, you are special. Okay? However, no matter how smart you are, if you were born before 1695, okay, when the calculus was invented, no matter how smart you are, you cannot study dynamic systems. How things evolve, how things change. No way, you don't have the clue. So best of mind, in that time they can only study some static situations and learning algebra and geometry, no matter how smart you are. Only when Newton method is invented, calculus you can do a dynamic model. So that you can see the world in a different way. That pushed the science significantly, right? Today we are here. We have fractional calculus as a tool. So how we should look at dynamic systems? So how we should revisit the way we are doing for the modeling using the traditional calculus? That's the question I want to ask you. So I want to hear good stories from you in your FISP presentations. Keep thinking from now. Now you have this. Don't you want to contribute something different? The reason is, you got a dynamic evolving system. Modeling controls. You always try to better categorize it, better control it, better model it. Okay? There are many ways to do the computation, to do the simulation. Okay? So I believe this is a new stage of science. Okay, new stage of science. If I look back, if I look back, okay, my contribution to this field is basically saying, look, using fractional order control or fractional modeling, I can do better than your best. Or in other words, my best is better than your best. So from engineering point of view, my job was focused on this part, philosophically. But there's another part missing. I'm not a scientist. So, is it possible that fractional calculus is the only way that can enable new science? New science, okay? In other words, you cannot gain that kind of level of understanding if you use integer order calculus. Okay? That part, I'm trying to educate more of you so that you answer it. We need to show that fractional calculus is the enabling tool for new sciences. Okay? New sciences. I hope you have new sciences. Okay? And you can see I have lots of slides, and this is only part of it. So this is my very traditional joke. So every time I do a presentation, I present a fractional set of slides to you. So this is a real fraction. Can you see this fraction here? Okay. I think I better stop here. I already prepared the homework for you, so check the email. And I check the crops every day. It's a good habit. I now start to check crops almost every day. Go there to see any message and to see any discussions. So I have more slides than you want. So, but I want to see something here. If I let you go, I have final slide to show. Okay. And in my lab, we had anniversary celebration last Saturday. I present a slide. I want to share one slide of this week regarding research excellence. So it's a presentation I really want to share with you. So, I started by saying that if you want a good job, you need hammering. So somebody's hammering. So I had this topic hammering. And so this one, I think is very important about education. So today, information is everywhere. If you go there and learn fractional calculus, just learn. But the question is, teachers can no longer throw information and facts at students. I cannot just throw information to you and overload your brain. And expect that education will occur. It will not happen. Okay? So that's why I like the word thinking. You need to give yourself enough time to think. That's why homework one is important. That's why I want you to remember FOT, fractional order thinking. So I'll let you go. I'll see you next time. Okay, and I'll share the slides and put them on my web. So I'll wait to fold it. Okay? All right, give me your quiz, please. Did you forget? Oh, I'm sorry. I should have gave you but it's okay. You can ignore it. But only when you want to get credits from me, you should send it. Otherwise, you don't have it. But if you give me next time, I give you back.
مرسی شما همینطور درس شب